So when addressing imbalance in categories or classes, we have to keep in mind that such imbalance or disproportionate number of samples may influence the calculations that are performed, calculations, estimations, inferences that are performed by the machine learning algorithm. So we're specifically discussing something that's pertinent for supervised learning with classification problems. And classification is in the domain of categorical statistical variables. So we may use the word class, meaning category or group. Imbalance occurs when data sets have a disproportionate ratio of observations in every group. In other words, when the number of samples per class is not equally distributed. So in such scenario, machine learning models may not work well with classes that are considered infrequent because there are not enough samples that are available to learn patterns, or because it would be difficult for the classifier to identify or to match such patterns. So a machine learning model may optimize on the dominant class, therefore creating some type of bias, because it might be sufficient to achieve good performance given the volume of the dominant class. So an illustration for imbalanced classes may be by considering a scenario of detection of fraud. For example, fraud detection in credit cards. Most of the credit card transactions are not fraud, and only a handful of transactions would be classified as fraud transactions. So here you may easily consider a hypothetical case where you may have a sample of 50 non-fraud transactions and one transaction that is classified as fraud. So that would give you a ratio of 50 to 1. Here is another illustration. We have a bar plot on the right side of the slide. So remember, as a bar plot, we are displaying along the horizontal axis categorical variables. In this case, the categories or groups they have numerical values, but they are 5 different groups with ratings, 5 stars, 4 stars, 3, 2, and 1. And then we can see this is based on product reviews, and we can see that the so-called 5-star reviews is really the dominant one. So we can see that there is almost like 50. So this is almost a stall here as 50. So maybe a little bit under 50, 45, 47 of such samples. And there are almost as many of, if you count the heights of the other ones, right? 4 stars is somewhat around here, and then the other 3 and 2 are about this level. So broadly speaking, if you count all the other samples, so you may say, well, just by eyeballing it, maybe there are maybe somewhere around 15 for this, and maybe like 7 and 7, more or less. This doesn't have to be very precise, right? So 15 plus 14, that's like 29, and maybe it is like another 3 of this. So there's like about a little more than 30 samples in all other 4 groups. And in this 5 rating alone, there is more than 40 samples or so on. So one approach when there is an imbalance is to update the performance metric. So for example, one may change the metric from accuracy to precision or to recall, or one may use the F1 score. But there are other techniques or approaches. One of them is called downsampling. This means that you take the dominant class, and even though this sounds maybe outrageous, you would remove observations, right? But you would do that in a way in which you're trying to mitigate the problem of imbalance, and you don't want to do that by adding an additional problem. So you would remove some observations in a way that does not introduce bias, or does not, you're perturbing, but you're trying to do it in the least perturbing way. In such case, you would be removing some observations uniformly at random without preference from, you're doing this removal from the dominant class, so that now the dominant class matches in size the other classes that are considered rare classes. So just to kind of reinforce, downsampling is about omitting certain samples, but doing that in a uniformly at random fashion. Now, the other technique is called upsampling. This means that for the classes that are considered rare, one would duplicate observations, but one would do this duplication also without adding bias or preference. The duplication of observations would also be done with this uniformly at random approach. More specifically, one would use the statistical sampling method called simple random sampling with replacement. The technique data generation is very similar to the upsampling methods. It's also called creating synthetic samples, or also referred as augmentation of data. It involves simple random sampling from the rare classes while slightly perturbing feature values to create new samples. And specifically, this type of technique has one name that's called synthetic minority oversampling technique. Another approach is to use weights, so that the learning algorithm would give more attention to rare classes in function of assigned weights. And in that sense, the dominant classes would receive lower weights, so that the algorithm would be less influenced by those classes. So specifically, the logistic regressor and the Python module sklearn provides an input parameter called class_weight, in which you may assign the weights to classes based on their frequencies. Remember, the frequencies is the count, the value count per class, which is illustrated in the bar plots with how high the A box of value counts may be.